In this video, I'm going to show you where the math functions are that you're going to need for some of the activities like the sine wave program, and then also some issues that arise when you are trying to exchange values between variables that have different sizes. So first, let's look at the math library. So all the math functions are in an object called math. So to see what's in the math library, just math dot, and then you'll see the IntelliSense here will show you everything that is in there. There's our sine, cosine, tangent, arc, cosine functions for doing exponents, logarithms, rounding. There's mathematical constants like pi and e. So that is all in the math library. So math dot whatever will get you some math function. All right, so there's, you want to take the square root of a number? There you go, math dot square root. And it says that it takes a double and returns you a double. So if you want to take the sine of something, math dot sine, there it is, sine. Now, it's worth mentioning when you do trigonometry, these trig functions do not work with degrees. They work with radians. So how do you convert from degrees to radians? Well, there are 2 pi radians in a circle, which is 360 degrees. There's 2 pi radians and 360 degrees. So if you divide 360 by 2 pi, you will get the conversion factor, which is 57.29. So something, something. So I always, just to convert from degrees to radians, I divide by this number. All right, so imagine that I want to take the sine of some angle. You know, I have an integer called angle, and it's going to run from, it's going to be between 0 and 360. And then maybe I have some result. I'll have a variable called result, and I'll set it to 0. And now what if I want to take the sine of the angle and do something with it? So let's, why is it griping at me? Okay, well, it's just saying it's never used. Fine. Yeah. Result equals angle, and then divided by 57.29, semicolon. All right. Now this seems like it should be a legitimate statement, right? But it's obviously giving us an error message. So let's talk about this error message and what we have to do to fix it. If we look at that definition for the sine function again, notice that it takes in a double as its parameter, and it returns us a double. So what's a double? This gets us into the sizes or the storage capacities of the different variable types. And we run into issues anytime we want to go from storing a number in a large data type into a smaller data type, because we risk losing precision. We risk, you know, the number not fitting, being truncated, or losing everything after the decimal place or something like that. So let's just kind of do a quick review of the sizes of some of these data types in C#. So the smallest one is the byte. Byte B equals 0. Bytes are 8 bits. 8 bits. There we go, it's a byte. Okay, now, what if what's another small data type? A char, a CH, a single letter. Now you might think that that's 8 bits also, and for many, many years they were, but C# or the .NET framework that it's part of uses 16 bits to store a letter, and that allows it to store, you know, not only English letters, but, you know, French and Spanish and German accents and math symbols and other stuff like that. So that's a char. A char is 16 bits. What else do we have that's 16 bits? Well, there's something called a short. It's a short integer. I'll call it SHRT or short. I can't. Yeah, I'll call it S. I'll call it S. Equals, 100. So this is a 16-bit number. The 16-bit number can store values if it's unsigned, means they're all positive, between 0 and 65535. That's the biggest number you could store in this. So watch this, 65535. Okay, cool. That will that work? It should. Cannot be converted to a short. Oh, interesting. Is it a U short? Ah, there we go. So a U short is don't even worry about signed and unsigned, but keep in mind you are limited to what you can store in a variable by the size of that variable. So a short is a number that actually goes from about negative 32,000 to positive 32,000. All right, and then integers are 32 bits. And they store values kind of between maybe negative 2 billion and positive 2 billion, something like that. There's 4 billion possible values, and integers can be positive or negative. So half of those values are negative and half of those are positive. And then let's look at some of our other 32-bit data types. A float is a number with a decimal point that is also 32 bits. So, a floating point, if you need a number with a decimal point in it, like, you know, it's not an integer, it's got a sort of fractional component or a decimal point. That's a float. Now, I'll get into this little error here in a sec, why it doesn't like this. And then, so that's a 32-bit data type. And what about doubles? Doubles are also numbers with decimal points. 3.1415, whatever it is, 29, I don't know, something like that. It's 59, 2.1415, I don't know. So this number is a 64-bit value, 64 bits long, 4 bytes, 4 bytes. Because there's 8 bits in a byte, 8 bits, 8 bytes, 8 bits in a byte. So divide 8 into 64, that's the number of bytes, 8 bytes long. Ints are 4 bytes long. So you can see what's going to happen. If I have a value in a double and I try to put it into a float, I'm taking something that is 64 bits and I'm trying to put it into something that's only 32 bits. Or put another way, I've got an 8-byte value and I'm trying to put it in a 4-byte value. And you can see that it's not going to fit. So that's where we get into something called typecasting or casting. Typecasting? Casting? Yes. So let's fix our and then let's look at this little error here. Why do we get this error? It says the literal of type double cannot be implicitly converted to a float. Use the F suffix to create a literal of this type. All right, so what does that mean? Well, when the compiler sees a number, a literal number like that, that's what that's called. When you just type in a number, it's a literal number. It assumes it's a double. It assumes it's 64 bits. Can I put a 64-bit value in a 32-bit space? No, I can't. So the way to indicate that this number is not 64 bits and is in fact a float, which is 32 bits, is to put an F after it. So now that error went away. So this literal here is 32 bits long because it's got the F on the end. This is 64 bits long because it does not have the F on the end. So there's the crash course in C# data types and their sizes. Now, how do I fix this problem of I'm going to do some calculation that returns a double and I need to put it into an integer? Well, you can see the error message, cannot convert a type double to an integer. An explicit conversion exists. Are you missing a cast? So what does it mean to cast? So a cast is an operator. It's like, like a minus sign. And you can change, you can tell the compiler that you understand that there's a danger of truncating your value, losing everything after the decimal point, but you're going to do it anyway. You don't care. So what this is called a cast. What it does is it takes this thing, the thing immediately to its right, and it converts it into this value temporarily, and then it can store it in the target. So if I don't have the cast, this returns a double. So this is a 64-bit result, and I can't put it in a 32-bit quantity. So I have to put in an explicit conversion that says, yes, I want you to smash this thing, this 64-bit thing, down into a 32-bit integer, and I want you to stuff it into result. So this is an explicit cast. And you need an explicit cast anytime you are going from a larger data type to a smaller data type, because there's a possibility you will risk losing precision. Now, what if I change this thing to a float? Does that solve the problem? No. Why not? Well, because this is 64 bits, and how big are floats? Floats are 32 bits. So again, I need an explicit conversion. I need to say, okay, take this thing and convert it to a float, which is a 32-bit number with a decimal point, and store it in result. So that is that's what this thing is. It's a typecast. When you need to convert from one side, when you need to go from a large data type to a smaller data type, you need to kind of downcast, or you need to cast like this. Now, and this happens when you're using the math library functions, because they do everything as doubles, and it returns you the largest data type you could possibly have. So one way to solve all this is just to use doubles. That might solve your problem, and then you don't need the cast. But there's times where you really do need to work with integers, and then you might want to do an integer cast. Now, here's an interesting thing. Let's just go in here. I'm going to put an F there. Why is there no problem here? Why is this fine? So angle's an integer. This is a floating point number. Why don't I get a problem here? Well, what the compiler will do is it will say, okay, hang on, this is an integer, and this is a floating point number. So it is going to probably upgrade this or promote this to a floating point number, or it will turn this thing temporarily into a floating point number, do the calculation, and then it will promote it to a double. So there's going to be all this kind of stuff that happens under the hood when you do this calculation. It's going to say, okay, hang on, I can't divide an integer by a floating point number. I have got to convert this to a floating point number too. So it'll say, okay, great, I'll do this as floating point numbers. Oh, and then look, the sine function requires a double. So now what I'll do is I'll convert this stuff into a double, and that's fine. And all that conversion is happening here, and you don't, without you having to worry about it. But the reason you don't have to worry about it is because this is a 32-bit quantity, and the sine function accepts a 64-bit quantity. In this case, you're giving you're not going to lose any precision if you supply a smaller quantity than what they're asking for. Because this thing wants a double, and it can take this float and promote it to a double. It can do that for you. It's without the risk of losing precision. It's when you're going the other way. You're going from a large data type that this returns down to a smaller data type. That is where you risk losing precision, and that's where the explicit cast has to happen. So you may run into this. Be aware of that. So the different variables types have different sizes. They have different storage capacities. And if you're trying to take a big value and put it into a smaller space, you will probably have to do a typecast in order to say, you know what, I understand that there's a risk of doing this, but I'm going to do it anyway. The other thing, remember this, convert from the temperature converter, convert dot to int32. That's an integer. That would convert the result of this to an integer. Right, so this is evaluated from the inside out. So, right, figure out whatever that is, take the sine of it, that returns a double, and then we're going to convert the double to a 32-bit integer. What if you wanted to go to a floating point number? Well, let's see what's in there. It's not the most obviously named thing, but it's certainly in there. That is I thought it was too single. Let's see. Yes, too single. To a single precision floating point number. That's a float. It's not a very well named thing, but so if I did 3.1415 and result is a float, this works, right? So this is a double, and then I'm passing it into the conversion function. It is converting it to a this should be called toFloat. ToSingle is a stupid name for it. And then so now it's going to return me back a 32-bit value, which will fit in this 32-bit value. So there you go. When you are going from larger data types down to smaller data types, you're going to have to explicitly cast using a cast operator like this. or using the convert class. If you are going from a smaller data type to a larger data type, you should not have to worry about it. The compiler will do that for you. It'll handle it for you. So there you go. That's how to use the math library, and that is also how to do type conversions using the cast operator.